Nuclear power plants are thermal power stations which generate electrical energy from heat. They consist of numerous buildings and facilities, the most important of which are as follows. The turbine building houses several turbines as well as the generator necessary for electrical power generation. The containment building where the nuclear reactor is housed is made of meter-thick reinforced concrete. Inside this building, nuclear reactions take place where water is heated up. The cooling tower, which can be as tall as 200 meters, is where hot water is cooled. In order to easily understand the underlying principles, the following is a description of the most important components of a nuclear power plant that uses a pressurized water reactor, PWR. In the reactor pressure vessel, the nuclear reaction and the associated release of thermal energy takes place. In a pressurized water reactor, as in this case, the reactor pressure vessel stands about 12 meters tall. The walls are about 25 centimeters thick. Inside is where the fuel assemblies can be found. In pressurized water reactors, about 150 such assemblies are installed. A single fuel assembly is composed of many fuel rods. A fuel rod is about 5 meters in length and has a diameter of about 23 centimeters. The actual nuclear fuel is found inside of each fuel rod. Small nuclear fuel pellets composed of enriched uranium or plutonium make nuclear fission chain reaction possible. In the fission chain reaction, thermal energy is released. Water is needed in order to absorb the thermal energy and keep the chain reaction going. Inside the vessel, the water is heated to over 570 degrees Fahrenheit. The water does not boil, however, since the pressurizer maintains the water pressure constant at around 160 bars. The heated water is eventually pumped to a heat exchanger, also called steam generator. These are typically in the form of a shell and tube heat exchanger. Hot water flows through the U-tubes, heating up the metal of the pipes so that any water inside the heat exchanger begins to boil. The resulting steam is eventually fed through a set of pipes to the turbine building. The steam first drives a high-pressure turbine and then is typically fed to 2 low-pressure turbines. All of the turbines are connected by a spinning shaft to the electrical generator, which in turn produces AC electricity from the shaft's rotational energy. The steam is converted again into liquid form in a condenser, and then returned back to the steam generator. The water needed for this often comes from an adjacent river, or is cooled in a cooling tower. The water circulation systems are always kept separate from one another. Water in the primary circulation system never leaves the containment building. This water is radioactive, since it has been in direct contact with the fuel rods. Water in the secondary circulation system is used to drive the turbines and is not radioactive. The cooling circulation system provides cool water.
This is Darlington, on the shores of Lake Ontario, about 70 kilometers east of Toronto. It's one of Ontario Power Generation's 2 nuclear generating stations. And it's basically a factory for making lots of electricity, enough to power a city of around 2 million people. That's about 20% of Ontario's electricity needs. The building is divided into 2 main areas along its length. the nuclear side with the reactors, and the conventional side with the turbine generators that make the electricity. There are 4 generating units at Darlington, units 1 to 4, each with a reactor and a turbine generator. Each unit can generate 935 megawatts of electricity. Darlington produces electricity using the heat that comes from splitting uranium atoms in a process called nuclear fission. The fuel is naturally occurring uranium that's processed into small pellets. The pellets are sealed into metal tubes, which are welded together to form a fuel bundle. The fuel bundles are then inserted into a large tank called a calandria, which is the heart of the nuclear reactor. In CANDU reactors, a special kind of water called heavy water flows around the fuel bundles. Heavy water is found in all water, rivers, lakes, and oceans. On average, 1 out of every 7,000 drops of water is heavy water. It's 10% heavier than ordinary water because it incorporates a heavy form of hydrogen called deuterium. The heavy water slows down tiny particles called neutrons, so they are more likely to hit and split the uranium atoms. A chain reaction of splitting atoms releases tremendous heat into the heavy water. The heated heavy water flows through a closed-loop system that's pumped through the reactor to a set of steam generators, where it transfers the heat to ordinary water. When that water boils, it turns into steam. The steam is transported at high pressure through pipes to a large turbine, where it pushes the blades and turns a shaft connected to a rotor in the generator, causing the rotor to spin. The spinning rotor is a large electromagnet that produces rotating magnetic fields. These fields move across coils of copper wire in the generator, producing electricity. The electricity is fed into transmission lines that carry the power from Darlington to people's homes and businesses. All used fuel is carefully stored in safe and secure areas that are constantly monitored by the Canadian Nuclear Safety Commission and the International Atomic Energy Agency. So let's take a tour of Darlington. Before going into the station, everyone has to pass through a security building that operates a lot like an airport security system. There are machines to check for explosive chemicals, X-ray machines, and metal detectors. Then everyone has to pass through a turnstile where their security card and their individual hand-bone structure must match. At all times, highly trained security staff inspect every person and everything entering and leaving the station. Then, all personnel pick up devices that are issued to them to constantly monitor for radiation while inside the station. Safety is the #1 priority at all Ontario power generation facilities. So everyone working in the station must have the proper protective equipment: safety glasses, hard hats, safety boots, gloves, and hearing protection. Visitors must also wear safety equipment. The main entry for the station is through an area known as Unit 0. This is where the common systems for the entire station are located: heating, lighting, ventilation, and the operations control room. Also located in Unit 0 are the mechanical maintenance shop, where experts in welding, machining, and pipe fitting work on equipment. The control maintenance shop for the experts in electrical, instrumentation, and electronic systems. And stores, where people pick up the tools and parts they need to do their job. The station is divided into zones according to the location of systems and equipment, to prevent the transfer of radioactive materials. Whenever people or equipment move from zone to zone, they monitor to ensure no transfer of radioactivity. Let's start at the beginning of the fission process, where heat is released from the fuel. Each of the 4 reactor buildings is made of heavily reinforced concrete, with external walls 2 meters thick. When a reactor's operating, no one can enter the reactor vault, but when it's shut down for maintenance, radiation fields decrease and trained staff can safely work here. Technicians put on protective equipment, log in with their tools, and then access the reactor through the airlock system. The reactor consists of a large, heavily shielded vessel, or calandria, which contains 480 fuel channels and 6,240 bundles of uranium fuel. We're now looking down on the top of the reactor vault. The process of nuclear fission draws the heat from the fuel to boil ordinary water into steam. All that steam is transferred over to the turbine side of the station through large steam lines. So this is the turbine hall. It's almost 4 football fields long and 19 stories high. All 4 turbine generating units are located in this one giant area. You can see the color coding. Unit 1 is red, Unit 2 is yellow, Unit 3 is green, and Unit 4 is purple. This color coding extends all the way through the systems for the unit and into the control room. Since all 4 generating units are identical, the color coding ensures correct unit and system identification. The turbine blades are shaped like a fan, where steam enters and turns the blades. In the center is a connecting shaft that rotates at 1,800 times a minute as the steam pushes the blades. At the very end is a relatively small piece of equipment, the actual generator where the electricity is made. From here, it's out to the grid and into homes and businesses. So finally, we come back to Unit 0 and the control room. Mission control for the whole station. Every important system in the plant is monitored and controlled from this room by highly trained and certified staff. Authorized nuclear operators go through an average of 8 years of high-level training and testing to become fully certified by the Canadian Nuclear Safety Commission. All Darlington staff are lifelong learners and spend up to 20% of their time in continual safety and job training. OPG nuclear generating stations use the Defense in-Depth Safety philosophy that sets the highest standards for plant design and operations. For critical components and systems, backup devices ensure redundancy at all times, as well as fast-acting shutdown systems. There is a secondary containment structure called the vacuum building. This 71-meter-high, 24-story cylindrical concrete structure is connected to the reactor buildings by a pressure relief duct and is a unique safety feature of the CANDO system. So, that's a look inside the massive machine that is the Darlington Nuclear Generating Station. But ultimately, that's not what makes the power. It takes people. Over 2,500 highly trained and skilled staff work at Darlington. 24 hours a day, 365 days a year, supplying the homes and businesses of Ontario with safe, reliable, clean electricity.
Nuclear reactor. In this video, we're going to learn about the nuclear reactor. Nuclear reactors are the modern-day devices extensively used for power generation, as the traditional fossil fuels, like coal, are at the breach of extinction. A nuclear reactor is the source of intense heat, which is in turn used for generation of power in nuclear power stations. Its mechanism is similar to that of a furnace in a steam generator. The steam is used to drive the turbines of the electric generator system. A nuclear reactor consists of three crucial components: fuel elements, moderator, and control rods. Fuel elements come usually in the shape of thin rods of about 1 centimeter in diameter and contain fissionable nuclei like uranium-235 or uranium-238. These rods vary in number according to the size of the reactor. In large power reactors, thousands of fuel elements are placed close to each other. This region where these fuel elements are placed is called the reactor core. These fuel elements are normally immersed in water, which acts as a moderator. The objective of a moderator is to slow down the energy neutrons in a nuclear reactor, which are produced during the nuclear fission process by the fuel elements. Thermal neutrons, which are the neutrons with energy of about 0.04 electron volts, are capable of producing fission reaction with uranium-235. During the fission reaction process, new neutrons are given out, which have energies of about 1 MeV. This is 1 mega electron volts. These neutrons typically escape from participating in another fission process, as they are accompanied by enormous energy release. In fact, the probability of these neutrons produce another fission reaction is 500 times less than that compared to a thermal neutron. This is where a moderator is extremely useful. Moderators have the capability to slow down, or in other words, moderate, the speeds of these high-energy neutrons so that they can in turn be used for a chain reaction to trigger multiple fission reactions of other uranium-235 nuclei. Commonly, ordinary or heavy water is used as a moderator in nuclear reactors because of the deuterons present in them, which are capable of slowing down the neutron speed. Water molecules in the moderator are useful in slowing down the high-energy neutrons, which leave the fuel element after nuclear fission. These high-energy neutrons collide with water molecules, thereby losing out on some energy with every collision and therefore slowing down substantially. A new fission reaction can now be triggered using this slow neutron by striking it with a fuel element. The third and most prominent part of a nuclear reactor are the control rods. In order to get a steady output of energy from the nuclear reactor, every single fission reaction should trigger another fission reaction and ensure the availability of spare neutrons released to trigger the chain reactions. By controlling the number of spare neutrons available at any given time, the rate of nuclear fission chain reactions can be controlled. This control on the fission reaction can be maintained using control rods. The main function of the control rods is to absorb any excess or spare neutron in the moderator in order to prevent any further fission reactions. Usually, such control rods are made of boron or cadmium. To increase the rate of fission reactions, these rods can be removed from the moderator. A steady output of energy can thus be maintained by inserting or removing the control rods in the nuclear reactor. Now that we know the components of a nuclear reactor, let's understand the working of a nuclear reactor. It's usually enclosed in a shield made of thick concrete walls. It consists of a reactor core, pump, and heat exchanger. The reactor core and pump are placed in contact with the water, which is usually the heat exchanger in these reactors. Due to the enormous amount of heat released during the fusion reaction, the surrounding water gets heated up and changes to steam, which is in turn used to turn the turbines. So huge heat energy gets converted into electrical energy. Water is continuously flown in and out of the nuclear reactor using the pump. So a nuclear reactor successfully generates nuclear energy from fission reactions.
Island of Japan. At 3:36 p.m., less than an hour after the earthquake, a tsunami swept over the coast. The waves went all the way up to 10 kilometers inland. Result: over 20,000 people dead or missing, destroyed towns, ports and land devastated. Nuclear power plants were also affected, one in particular, namely the Fukushima Daiichi. Fukushima Daiichi is 250 kilometers northeast of Tokyo. The nuclear power plant has 6 reactors, each reactor successively commissioned during the 1970s. Units 1, 2, and 3 were operating at full power. The core in Unit 4 was unloaded. Units 5 and 6 were in cold shutdown. Fukushima reactors have a different technology than the pressurized water reactors built by the French operator EDF. They are boiling water reactors called BWRs. We say reactor because the heat in the core is produced by fission reactions. Boiling water because the water that removes the heat from the core turns into steam, and the steam goes directly to the turbine. The turbine drives the generator that produces electricity. Afterwards, the steam is condensed with the help of a seawater cooling system and returns to the core. A boiling water reactor has only one single system combining feed water and steam. The core is composed of fuel assemblies containing uranium. It is controlled by control rods introduced from the bottom that can stop the fission reactions in case of an emergency. Fission of uranium nuclei produces radioactive atoms that in turn produce heat, and this continues to occur even after reactor shutdown. This is called residual heat. Keeping the fuel confined and cooled is a major safety issue. The fuel is isolated from the environment by different containment barriers, just like the famous Russian dolls. A first barrier, the fuel cladding of zirconium alloy. A second barrier, the steel reactor vessel in combination with steam and water cooling systems. Finally, the third barrier, the containment building in concrete with a leak-tight steel liner. The fuel is kept under water in the reactor as well as in the adjacent pool where the spent fuel is unloaded. The pool is located at the top of the reactor vessel to facilitate the transfer of fuel underwater. When the earthquake hit the coast, seismic sensors triggered the insertion of control rods. Although fission reactions stopped, the residual heat had to be removed. The off-site power supply was lost, and the emergency diesel generators took over automatically. They supply electricity to the backup systems needed for core cooling. In reactors 2 and 3, it is a turbopump. The steam generated by the reactor operates the turbopump, which feeds water into the reactor vessel. The steam is condensed in the wet well suppression pool within the containment. In reactor 1, there was no turbopump, but a heat exchanger, which condensed steam from the reactor vessel. The condensed water was reintroduced into the reactor vessel by gravity. This heat exchanger provided core cooling by natural convection for more than 10 hours. Until then, everything seemed under control. However, reactor 1, due to excessive cooling, forced the operators to temporarily isolate the heat exchanger in compliance with operating procedures. The tsunami wave arrived less than an hour after the earthquake. The waves went over the seawall, flooding the lower parts of buildings and disabled the emergency diesel generators. On reactor 1, the operator was unable to reactivate the heat exchanger. The core was no longer cooled. It would be the first to melt. On units 2 and 3, the batteries were still operational. They operated some of the valves. The turbine-driven pumps ran for nearly 24 hours and then stopped. The cores were no longer cooled. The meltdown scenario is almost the same in all three reactors, only the dates change. The water in the reactor vessel evaporated. The fuel became uncovered. Heated up to a temperature of 2,300 degrees Celsius, the fuel melted and mixed with the materials from the structure to form a magma called corium. The corium flowed down to the bottom of the reactor vessel. According to Japanese officials, it pierced the reactor vessel before falling on the concrete basemat inside the containment. What quantity of corium fell? How deep did it erode the concrete? Did it pierce the steel liner? Even today, it is not possible to learn more about the state of the corium in the three reactors. At the same time, still in the reactor vessel, the steam was loaded with radioactive elements and hydrogen. To explain this phenomenon, let's have a look at the early stages of fuel degradation. Heated at high temperature, the fuel cladding is oxidized and cracks, releasing volatile radioactive elements. In addition to this, the zirconium of the fuel clad created a reaction with the steam by absorbing the oxygen and by releasing hydrogen. Normally, when mixed with air, hydrogen catches fire and explodes. However, the containment building was filled with nitrogen, an inert gas that avoids the presence of oxygen. At this stage, there was no risk. As the steam pressure rose to a dangerous level in the reactor vessel, the depressurizing valves opened. Gas was forced into the wet well suppression pool by a venting line. The water acted as an efficient filter by trapping much of the radioactive elements. But the water was no longer cooled because the emergency diesel generators were out of order, and it soon began to boil, thereby reducing its filtration capacity. The wet well suppression pool and the communicating containment began to enter into an overpressure situation. To avoid containment rupture, the operator decided to release the gas into the atmosphere. Normally, the venting line should have led all the gas outside the building by the chimney of the plant. But hydrogen was escaping through uncontrolled leakage pathways and was released into the reactor building. Hydrogen reacts violently with oxygen in the air. The explosion blew apart the frame at the top of the building, apparently without damaging the containment building. Radioactive elements not yet trapped in the wet well suppression pool were released into the environment. Due to the absence of usable fresh water on the site, the operators decided to inject seawater into the reactor vessel. This solution, far from ideal, since salt is chemically active, had at least the advantage of cooling and stabilizing the corium. In the 4 days following the tsunami, the 4 reactors were damaged by explosions, and 3 of them with core melt. Although it has kept its structure intact, Reactor 2 is the current source of the most important radioactive releases into the soil as well as into the sea. The explosion took place inside the building. Operators have probably encountered difficulties depressurizing the containment, and the wet well suppression pool broke. This loss of leak tightness led to the discharge into the atmosphere of unfiltered radioactive elements and to the spreading of highly contaminated water in the buildings, leading to highly polluting discharges into the sea. The explosion of Reactor 4 was due to hydrogen, even though the core was completely unloaded. The hydrogen came from Reactor 3 via a joint pipe. The reactor's storage pools were also a great concern because they had lost their cooling systems, and in addition to this, they were not protected by any containment. Very little spent fuel was stored in Pool 1. However, there was much more in Pools 2, 3, and 4, especially Pool 4, which contained the equivalent of the 3 cores. In all 3 pools, the water started to boil, and without the help in extremis of cold water from helicopters and from a fire hose, the spent fuel would have caused considerable radioactive release into the environment. Gradually, the situation began to stabilize. By the end of March 2011, fresh water had replaced seawater. In July, the reactor cooling system was again in operation in closed circuit, thereby avoiding discharges of contaminated water into the environment. In December 2011, Japanese authorities officially declared that the nuclear power plant reached the cold shutdown state, an expression used when the cooling water does not evaporate anymore and remains liquid below 100 degrees Celsius. This nuclear crisis was managed by men working under extremely difficult conditions, cut off from the rest of the world, with no news from their families after the tsunami, without any power supply, threatened by radiation. They fought with all their force to cool the reactors, trying to make, in vain, the backup systems work again, or by using improvised means. After this race against time to cool the plant, followed a year where about 20,000 workers succeeded each other, trying to regain control of the plant by, first, enhancing the dike against another tsunami, mapping the site contamination, clearing every access to the site, immobilizing radioactive dust, treating and disposing of contaminated water, and avoiding further radioactive release. In the years ahead, the challenge will be to remove the spent fuel from the pools for final storage in radioactive waste repositories. And then eventually, on the long term, under the critical eye of international experts, the issue will give way to a challenge, namely to remove the melted fuel from the 3 damaged reactors and to dismantle the site. As we can see, a huge task awaits the Japanese, a task